Let's get started, and Elijah continues from last time.
Okay. Let me just rather briefly recall where we were, starting with just a reminder of some of the notation. So we had our G complex semi-simple Lie algebra, roots, simple roots. We had a weight lattice. And I was writing D for the index of the root lattice and the weight lattice. We had the quantum enveloping algebra, which we were writing as U as usual. And inside of that, we had U plus, which was the subalgebra generated by the E alphas, and U minus, which was the subalgebra generated by the F alphas. And I guess I should also say, just as a reminder, K was our field, and Q in K was assumed transcendental over the prime subfield. K is characteristic 0. And we were assuming that Q to the 1 over D was in our field. Then from our rune stock, we had this pairing between U minus and U plus, and this was non-degenerate. So that allowed us to choose dual bases, VI mu and UI mu, with respect to this pairing for every, so I'll write just as a reminder that the VI mu's, these were in U minus the mu graded part, and UI mu's were in the U plus mu part. And then we defined theta mu just to be the sum over dual bases. And we defined for W and V finite dimensional type 1 representations for the quantum enveloping algebra, this theta sub WV as the sum over mu in the roots, in the root lattice, which were greater than or equal to 0. And then we summed theta mu's restricted to their action, just looking at their action on W tensor V. And this was in order to define this R matrix. There was one other ingredient, this map F tilde, which was somehow defined so that for each tensor product, W tensor V, we had a map from W tensor V to W tensor V, which if I had little w, little v inside of the W lambda 1 tensor V lambda 2 weight space, this mapped to Q to the negative lambda mu times W tensor V, where this parentheses, this is the W invariant bilinear pairing on the weight lattice. And the reason we needed to have this Q to the 1 over D was because there might be a D in the denominator of this expression when lambda and mu are arbitrary weights. This is avoided if they're weights that are in the root lattice, but we're thinking about all weights. And then this allowed us to define R sub VW. This was like our braiding between V tensor W and W tensor V to be the composition theta WV of F tilde of P. And this was a map from V tensor W to W tensor V. And last time I had stated and outlined some of the proof of this theorem that RVW is a U module isomorphism, and it's functorial in V and W. So I mentioned that really the main thing to do here is prove that this is a U module map. And we broke that into 3 steps. So we needed to show this first step, which is what I'll actually prove in a moment. This is delta of U composed with theta is equal to tau delta of U post-composed with theta. And this is where tau delta, just as a reminder, was tau tensor tau composed with delta composed with tau. And tau was this anti-automorphism of the enveloping algebra that fixed E and F and sent K to K inverse. So we had delta, we had this tau twisted delta, and we also had delta op. And that factored into the other steps. So we have to also show that tau delta U of F tilde is F tilde of delta op of U, and P of U acting on a vector X is equal to delta op of U P of X. So these 3 steps will allow us to conclude that RVW commutes with the action of U. So I left it last time as an exercise just to check steps 2 and 3, both rather easy. And then I discussed how to use steps 1, 2, and 3 to actually argue that you have RVW of U acting on X is equal to U acting on RVW of X. So even though I did that last time, I'll just say it's a useful exercise to maybe do one more time on your own, just to see how that worked. So now this is the main thing that we needed to do at the start of today, the proof of 1. So 1 here says that the co-multiplication and theta, when you interchange those, you get theta and then this tau twisted co-multiplication. So the first thing is, instead of checking it for all U, it suffices to check on generators. And since this element theta is degree 0 in U tensor U, since it's the sum over dual bases for U mu and U, the U mu weight space in U plus, and the negative mu weight space in U minus, plus the fact that delta of K alpha is the same as the tau twisted delta of K alpha. This implies that theta of tau delta of K alpha is delta of K alpha of theta. So it's basically the point of this is just, it's easy to check it on the generators in the quantum carton or whatever you want to call it, the degree 0 part, just the K elements. And then we're going to work a little bit more to check it for the E's, and the F's are similar. So U equals E alpha and U equals F alpha are similar. So we focus just on the E alphas. And then there's one more reduction at this point, which is it suffices to show, and the reason is because theta is this sum of theta mu's, it suffices to show that the following equation holds. So if I do E alpha tensor 1 theta mu plus K alpha tensor E alpha theta mu minus alpha, that's equal to theta mu E alpha tensor 1 plus theta mu minus alpha K alpha inverse tensor E alpha. So let me comment on this equation. Sorry, my pad just froze for a second. So this is what we will show. This is sufficient because, well, theta is this sum over theta mu's. So once we sum over all theta mu's, the mu and the mu minus alpha sort of, it doesn't matter that they're in the same equation. We just get that this term on the left-hand side, E alpha tensor 1 plus K alpha tensor E alpha, composed with theta is equal to theta composed with E alpha tensor 1 plus K alpha inverse tensor E alpha. And the point is that this term is delta of E alpha, and this term is tau delta of E alpha. So we just need, we're reduced to showing this equality. There's a similar equation for the F's, but then the proof for the F's will be, we'll run sort of in parallel to this. So we're just going to do it for ease. So where do we start? So start with just rearranging this equation. So this equation is in the form that makes the most sense from what we were trying to show, but we start just by rearranging it as thinking about E alpha tensor 1 composed with theta mu minus theta mu composed with E alpha tensor 1. So we just move the theta mu's to one side, and we're going to try to transform this so that we have then moved the theta mu minus alphas to the other side. And by definition, the theta mu's are sum over dual basis elements. So this is equal to, I sum, and I have E alpha tensor, times VI mu minus VI mu E alpha tensor UI mu. So I'm just expanding theta mu as the sum of the VI mu's in U minus and the UI mu's in U plus, summing over these dual basis elements. And then there's some work to do that's basically was already done in Arun's talk. And so we use the following. So lemma 6.17 tells us that for an element y in U minus mu minus alpha a simple root and mu in Z phi, so exactly the situation that we're in, where y we should think of as being the VI mu. We have E alpha y minus y E alpha, which is this, I mean, basically this catered to exactly dealing with this term here, is equal to something called C alpha, which I'll have to explain, times K alpha times R alpha of y, which I'll have to remind us about, minus R alpha prime of y, which we have to be reminded of, times K alpha inverse. So we already saw some E alpha y minus y E alpha term in chapter 6 in our Runstock, and so I'm just needing to recall what all of this on the right-hand side was. So C alpha was Q alpha minus Q alpha inverse minus that inverse. So it was minus 1 over Q alpha minus Q alpha inverse. And then how did we make sense of the R alphas and the R alpha primes? Well, we started by noting that if y is in u minus mu minus, then delta of y is in, well, we had this direct sum decomposition of nu less between mu and 0. Nu is a root. U minus nu minus tensor u minus mu minus nu minus k nu inverse. And that told us that we have elements R alpha of y and R alpha prime of y in u minus mu minus alpha, satisfying, I can write delta of y in terms of this direct sum as y tensor k mu inverse plus, and then I sum just over simple roots. And these are where my R alpha y's live. Tensor f alpha k mu minus alpha inverse plus the rest of the terms. And I also have that delta of y is, I can write this as 1 tensor y plus the sum over simple roots. And now move my r to the, or move these terms to the other side, and I get R alpha primes. These are defined via this formula. So my R alpha of y and my R alpha prime of y are defined by expanding delta of y in this direct sum and then projecting onto some component. So the definition was in 6.15 in Janssen's book. So that means that we can just rewrite what we had before, which was E alpha tensor 1 theta mu minus theta mu E alpha tensor 1 as, using this formula, we have a negative C alpha coming in, and then we sum K alpha, and we were going to use the R alphas. This is VI mu minus R alpha prime VI mu K alpha. And then we tensor with UI mu. So all of the work of introducing the R alphas and R alpha primes was just to get
Could
this.
you scroll up a little bit?
Scroll up, yes.
Why do I get minus C alpha? Well, because before I have had plus C alpha. And also I think K alpha in the second sum should be 2 power minus 1 in the bottom.
Yes, yes, that's true. The minus looks just wrong. but I do need an inverse here. Thank you.
Thanks.
Now, at this point, we're not going to use any properties of the R alphas. So we introduce these R alphas. They have some nice features, but we're not going to use them at the moment. Right now, we're just going to do the usual kind of sum over dual bases trick. So if I had y is in u of minus mu minus alpha, so that's where the R alpha of vi mu's are, then I would have y equals, and I can rewrite this as a sum of, I take y and I pair it against uj. This is now my basis that I've fixed in the mu minus alpha component of u plus, and then times vj, the basis that I fixed in the minus mu minus alpha component of u minus. So I can just expand out that y, and so I can apply that here and expand the R alpha vi mu's and the R alpha prime vi mu's. And that gives me, let me give myself a little bit more space. So this is then, the next line is, this is C alpha. I have a sum, and then this is going to be, I guess, a sum over I. K alpha, I sum over J. I'm using my pairing. This is R alpha of vi mu, uj, mu minus alpha, vj, mu minus alpha. And then I subtract from that sum over j, R alpha prime, vi mu, uj, mu minus alpha, vj mu minus alpha. And then I have a k alpha inverse. And then I tensor with ui mu. So I use the pairing and the dual bases to expand the R alpha of vi mu's. And then this is where we're going to use some property that was proved earlier. So in section 6.15, if you want a reference, or in Arun's talk, we checked that R alpha of y x is 1 over C alpha y E alpha x, and that R alpha prime of y x is 1 over C alpha y x E alpha. So you can see that this exactly allows us to move our E alphas from one side of the thetas to the other, basically. So
maybe we'll just leave the rest as an exercise.
Yeah. So basically, you use this formula to move them to the other side, and then use dual bases type tech. Use this. Use the argument backwards to re-expand it is what we want. So the rest is left as an exercise. Yeah, switch order of summation, put things back together. So that tells us that the R VWs commute with the action of U. And so we have basically one thing left to prove, and that's this other theorem that I promised, that also the R's will satisfy the hexagon equations. So theorem 2 is that this R, which is the theta composed with the F tilde composed with the P, satisfies the hexagon equations. And as usual, we're just going to check one of them. The other has a similar type of argument, and we will fix some notation for the proof. So let m prime, m double prime be some finite dimensional type 1 U modules. And we want to show that this diagram from last time commutes. So I'll write out the diagram and I'll leave filling in the maps from last time just as a mental exercise. And then I'll write down what we actually want to show in terms of morphisms. So we want to show that this diagram commutes. And what that translates to is that we need to show the equality of R M tensor M prime, comma M double prime is equal to, when I apply it to a vector, is equal to R M double prime tensor the identity composed with the identity tensor R M prime M double prime. So we need to show this equality of morphisms built out of these various R isomorphisms. And so when we're just, the first thing I'm going to do is rewrite this in terms of the definitions of the R's. And I'll go one step at a time. The first thing I'll do is focus on the top of the diagram, which is this side. And this is, I need to think about theta tensor 1 composed with F tilde tensor 1 composed with P tensor 1. This is, I'm applying my R to the first two components. And then I compose with 1 tensor theta, 1 tensor F tilde, and 1 tensor P. So I need to find, I just need to kind of work with this equation to rearrange it so that I can show that it's equal to what this is. So the rearranging of this side is just going to go in 3 stages. The first thing is if I were to write, so if theta was something like the sum of AI tensor BI, then I would write theta 1, 3 for sum of AI tensor 1 tensor BI. And so, in other words, I can think of theta 1, 3 as being conjugating 1 tensor theta by some flips. So I'm going to be able to use this to kind of commute this P tensor 1 flip past my 1 tensor theta, but I have to then introduce this theta 1, 3 notation to keep track of that I did that. And then the second thing is that similarly, we can think about if I write F1, 3 tilde, to take m prime, m double prime in the m lambda 1 tensor, m prime lambda 2 tensor, m double prime lambda 3 weight space, this is going to be defined as f of, I just only keep track of the first and third weight. So I'm just defining this notation, and then I can think of this similarly as being conjugated by the p's. So this is f13 tilde is actually p tensor 1 tensor f tilde, p tensor 1. So that allows me to commute the 1 tensor f tilde past a p tensor 1. And then the third thing is, if I write theta prime as the sum over mu's theta mu 1, 3, composed with 1 tensor k mu tensor 1, then you can check that theta prime of f tilde tensor 1 is f tilde tensor 1 of theta 1, 3. So this theta prime, it has some correction factor in terms of a k, since the weight is changing when I commute my theta 1, 3 past an f tilde tensor 1. And then you can use 1, 2, and 3 to transform this equation into make the top of the diagram equal to, I have theta tensor 1, theta prime, f tilde tensor 1, f13 tilde, p tensor 1, and 1 tensor p. So what I'm doing is I've got 3 things in here. I have some p's, I have some f's, and I have some thetas. The bottom of my diagram is going to be all thetas on the left, all f's in the middle, and all the p's on the right. So I'm just kind of rewriting things. Just in basic, here I'm sort of just inventing notation so that I can put some thetas on the left, some f's in the middle, and some p's on the right to make this look like a single R matrix, or a single braiding matrix. And then to actually deduce the hexagon equation, I'll just look at the bottom of the diagram. This is going to be, we need to look at R m tensor m prime comma m double prime, and that's theta m double prime m tensor m prime of f tilde of p, and here this p swaps. I treat the first 2 factors on their own, and then m double prime. And in order to basically get things to work out, I can tell that this p matches this p. So those are just these compositions of the linear maps that flip tensor factors. So I just need to check the connection between these f's and this f, and these thetas and this theta. So for the f's, it follows from some of it's essentially by definition following from some of the relations that we imposed on the f's. So f tilde was, if I plug in m double prime, m tensor m prime, this is just defined in this context as...
Wait, maybe we can skip checking this because it's you actually gave a definition of f tilde. and then it's just some equality of pairings of weights.
Sure.
And perhaps everybody can do it on their own.
Okay. Okay. Yeah. So I'll just write what we need. We just want f tilde tensor 1 of f13 tilde equal to this new f tilde. And that it follows from this equality where the f of lambda, I mean, it's the pairing of the weights. And then the second thing that we want is, I mean, as you can tell, we need to show that, well, let me just say one thing, that what is theta m double prime m tensor m prime? This is, I take one tensor, the co-multiplication, and get theta to act on that. So theta's, I have three things in my tensor product. Theta's acting on the first and on the tensor product of the second and third. And so I use this co-multiplication to get that to work right. And you need to check that this is theta tensor 1 composed with theta prime, which theta prime is where what I defined above. So this actually does take an argument. It's, you know, so to check the check, we need to verify that one tensor delta, again, instead of looking at all of theta at once, we just look at one of the theta mu's. So you need to verify that this is 0 less than or equal to nu less than or equal to mu, theta mu minus nu tensor 1 composed with, and here miraculously you see this k appearing that we had above in the theta prime. And I shouldn't say miraculously, but we have the k appearing that we had above, and then theta nu 1, 3. And to do this, you use that delta of x is, so we can just expand it in terms of that, so we had where delta of x lived above, it was in this u plus k nu tensor u plus term, and we can expand it in that term and then use the dual bases to write this as a sum of I, j, nu, vi, mu minus nu, vj, nu, x, ui, mu minus nu, k nu, tensor, uj nu. And this is for x in u mu plus. So this verification is, I guess, also left as exercise.
But perhaps an important point is that here we use that our pairing is a Hopf pairing, right? Mm-hmm. Because we somehow need to relate delta and this dual basis. That's a basic property behind this verification.
And okay, so that's establishing these two things that we needed to establish. So we saw that this R is one, you know, with the nice choice of function f that we used, which was just q to the pairing of lambda and mu, that gave us our f tilde. We have our theta, which is defined in terms of the pairing, and we have our flip map. This is our R. It's an isomorphism from V tensor W to W tensor V it's functorial in W and V, and it satisfies the hexagon equations. So as I outlined last time, all of those as a package tell us that this element R gives us an action of the braid group on endomorphisms of V tensor V, as well as V tensor V tensor V. So we're just going to explore that a little bit more carefully in the next setting. So before I go on, are there any questions about these two arguments? Good. Okay. So the next section is on Heca algebras and this sort of quantum version of the Schur-Weil duality. So I start with a reminder of the usual Schur-Weil duality.
Is this also a part of chapter 7?
This is a part of chapter 7. Do you want me to tell you the actual section number?
No, it's okay. It's okay. Yes.
Yeah. So the way that it goes, I am following the outline of chapter 7. That Janssen proves that these thetas, or the R's, satisfy that they're a U module isomorphism, checks the hexagon equations, and goes into this Schur-Weil duality, and then ends with the quantum coordinate algebra. So my exposition basically follows his in that way.
Got it. Thanks.
Yeah. So the usual Schur-Weil duality says that if I think about an n-dimensional vector space just over the complex numbers for us, and I tensor it with itself d times, there's two actions on this vector space. The first is I have SLN. So SLN acts on Cn, and SLN is, the universal enveloping algebra of SLN is a Hopf algebra, so it acts on the tensor product of Cn with itself so many times. And I also have the action of the symmetric group on D letters, and this action is permuting tensor factors. And these two actions commute, and one way of seeing that is the fact that delta equals delta op for just the classical enveloping algebra of SLN. And the theorem, let me actually introduce one thing before I said that. So this, as the permuting tensor factors action, remember that the symmetric group on D letters, it has this Coxeter presentation with simple reflections, SI, and these simple reflections map to, in terms of my P maps, I take the identity tensor P, tensor the identity, where this P acts on the I and I plus first terms. So I swap the I and the I plus first tensor factors, and that's giving me the action of these generators in my symmetric group. So the theorem that's just motivation for us is that the action of the symmetric group gives me an algebra homomorphism from the group algebra of the symmetric group to end over SLN of C to the n tensor D. And this is, the theorem is just that it's surjective, as well as there's some control, some description of the kernel. So this is just motivation. It's the classical story. And we already know what the quantum analog of the special linear group is. This is this generators and relations algebra UQ-SLN that we've been studying. And we just need to introduce what the quantum analog of the symmetric group is. So that's what I'll do next. So I need to make a definition. I'm going to write H sub D. And yeah, for now, I'm going to write it this way, H sub dt. So there's a parameter t. This is, I take z adjoin t plus or minus 1. I take the braid group, the group algebra of the braid group over this ring, and I quotient by the ideal generated by this quadratic relation. So I will take the braid group element, and if I square it, I'm going to set this equal to t inverse minus t, sigma I plus 1. So this is this Hecke algebra quadratic relation that I'm imposing on this algebra. And this is, so let me write D is the Hecke algebra and it depends on D, so should probably say something like that, like Hecke algebra on D strands or however you want to say it. But the point is that this Hecke algebra appears to have various specializations. If I were to write H sub D when t is equal to 1, well, my quadratic relation in that case would become sigma I squared is equal to 1. And then we're just going to be comparing this quotient of the braid group where the braids square to the identity and this Hecke algebra. So this is actually isomorphic to the integral group ring for the symmetric group on D letters. And even better, this is actually, it's the case that H sub dt is free over z adjoin tt inverse. So it's a free z tt inverse module of rank d factorial. So it has the same dimension as the symmetric group for all values of t. And there's other places that this algebra arises, but this is sort of all we need to know about it for now. It's just a quotient. It's a quotient of the group algebra of the braid group by this quadratic relation, such that if I take that quadratic relation and set t equal to 1, I recover the usual symmetric group. And we're going to see that it will replace the group algebra of the symmetric group in this Schur-Weil duality once I replace SLN with UQSLN and CN with the quantum version of the vector representation. So this quantum Schur-Weil duality still in this section, U is going to be UQSLN, and V will be the first fundamental representation. So this is the quantum version of the vector representation. So I can take V and tensor with the self D times. This is the analog of C to the n tensor D above. And I no longer have that the transposition that just flips tensor factors will commute with the action of U, but I have the obvious substitute based off of what we did above is going to be this map Ri from V tensor D to V tensor D, where Ri is defined as I take the identity and then I plug in RVV so that this is acting on the I and I plus first terms. So because we checked the hexagon equation, and we argued that the hexagon equation plus functoriality implies the braid relation, we're going to have that Ri plus 1 Ri is equal to Ri plus 1 Ri plus 1. That's okay. We also know that Ri Rj is equal to Rj, Ri, whenever I minus j has absolute value greater than or 1. If these I and j, if the Ri and Rj are acting on distant tensor factors, then the action just commutes. And these two checks tell us that, ignoring what we said above about Hecke algebras, we do actually get a map from the braid group to end U of V tensor D. And that's just sending the braid group generator sigma I to Ri. So I check the relations in the braid group based off of this Artin presentation. And then because the braid group's given by generators and relations, that's all I need to do. I get a map from the braid group to this endomorphism algebra. So what's left in order to just compare this to the Hecke algebra is this quadratic relation. So for the quadratic relation, we just look at an example for this lecture of SL2. The reason is that this is the example that I kind of computed for us above. So in this case, RVV was, there's a matrix, 4x4 matrix with q to the negative 1/2, 0, q to the 1/2, q to the negative 1/2 minus q to the 3/2, q to the 1/2, and q to the negative 1/2. So this is this 2x2 block in the middle, and then I have q to the negative 1/2 at the 1, 1, and 4, 4 spots. And so it's just a simple exercise to check that if I did r minus q to the negative 1/2, so this matrix, I would get rid of these terms and then have some different terms on my 2x2 block. And if I take that and multiply it by r plus q to the 3/2, so that adding 3/2, I would no longer have zeros here, but I had zeros on the other matrix. So my calculation is still just on this 2x2 block. And adding 3/2 will cancel this out and put something here. But if I multiply those two matrices together, I'll just get 0. So that's something you can check on at home. And that tells us that if I do q to the negative 1/2 r minus q inverse times q to the negative 1/2 r plus q, I get 0. So it's not actually these elements R that are giving me this Hecke relation exactly on the nose, because if I were to compute R squared, the exercise tells us that I don't get Q inverse minus Q plus times R plus 1. I get something else. So I have to rescale my element R by this Q to the negative 1/2 to get the exact Hecke relation. So now what we'll do is, I guess this is sort of really still in this example, let T equal to Q. So I'm specializing the group algebra of the braid group to my field K, and I'll also be specializing my Hecke algebra to my field K by setting T equal to Q, and I get the following. So I have the group algebra of the braid group over my field K. This still has a map to end U of V tensor D, but it's just slightly different. Now sigma I is going to Q to the negative 1/2 R. This definitely quotients, just by definition, onto K tensor, the Hecke algebra T. So this is the specialization of T to Q that I had in mind above. And by the check here, since I checked that this quadratic relation actually holds inside of end of V tensor V, this induces a map here, where the generator of the Hecke algebra sigma I bar, so just the quotient of the braid group generator in the Hecke algebra, this maps to Q to the negative 1/2 R. Ri, sorry for that. So these are the Ri's acting on the I and I plus first tensor factor. But it doesn't change what the quadratic relation will be. So the theorem then which I'm attributing based off of what I read in Janssen to Jimbo, is that K tensor HDT actually surjects onto end U of V tensor D, and there's some description of the kernel. And then
and
just
you need to put the assumptions that Q is not a root of unity.
Right.
At least not a root of unity of sufficiently small order.
So let me yeah, so still K is such that characteristic of K is 0 and Q is generic.
Well, that's actually not important, the characteristic. What's important is that Q is not a root of unity up to order n.
Okay. So I was hoping I'm not going to prove that this is surjective. I mean, I didn't even prove the classical version, but the comment is that for Q transcendental, the result, so if you remember, we kind of did an analogous argument where we used the classical case to imply something about the quantum case when Q was transcendental in the second talk that Leo gave. So this result follows from the classical case. And then I guess I maybe had an incorrect remark. Yvonne, you can correct me, but I thought that the result was actually still true when Q is any root of unity.
Well, but you need to deal with the Lustig's form of the quantum group.
Yeah, okay. Okay, yeah, so maybe when U is enlarged to, I don't know what our notation in this is for the divided powers group, but okay. So it's almost at the hour, so let me just state this exercise and then we can pause and I'll finish after that. So the exercise is that I did some calculations above when G was SL3. We have theta alpha, theta beta, and theta alpha plus beta. So you can check that Q to the negative 1/3 R squared is Q inverse minus Q times Q to the negative 1/3 R plus 1. So in order to get the R matrix to satisfy the hexagon equations, we had to introduce these roots of unity, but then the Hecke relation, if you rescale R, it doesn't actually have the root of unity or not the root of unity, the nth root in the relation. So that's all this check was about. So can I pause here and then talk about the quantum coordinate algebra after?
Yep, so let's make a 10 minutes break and resume at 5:10. And meanwhile, do people have questions?
Can we say a word on how the surjection is proven?
In which case?
in even just SL2?
In the quantum case, you mean?
Yes, yes.
Well, you know, somehow you deal with, so what do you do? So you have a flat deformation of your representation, and then you have a flat deformation of the algebra on the left, and you consider endomorphisms on the right. So when you deform, endomorphisms can only become smaller, and the image of a homomorphism can only become larger. So if you know that you have a surjection at a special point, then you know that you have a surjection at a generic point.
So it follows from the classical.
That's right.
Case.
When Q is a risky generic.
And it's another naive question. If we move to other type of semi-simple algebra to start with, does that correspond to other types of Hecke algebra?
No, if you want other types of Hecke algebras, he will need to do something different, and this I quantum groups.
So type A correspond to type A is just a correspondence.
So
it's just a coincidence.
No, I mean, it's not a coincidence. Well, the point is that, you know, you can ask what kind of sure-wide duality you get when you have a semi-simple algebra of classical type, and you can describe what you get on the left-hand side. You will get Brouwer algebras, but they're not Hecke algebras. So if you want Hecke algebras, if you want group algebras of the symmetric groups, of Weil groups, in the classical sure-wide duality, you need to do something else. You cannot just take a classical group and take endomorphisms of times the power of its defining representation. It's just not going to work.
I see. Yeah, I should definitely look into type B, C, D, even in the classical case. Thank you.
Yep. Okay, there was a question from Joe in the chat, which was already answered by Raphael.
Yeah, I have a question. So you mentioned this. What is I quantum groups? Can you remind me what this is?
That's quantization of so how does this work? It's quantized symmetric pair. So it's a certain co-ideal subalgebra in the usual quantum group of
no, this is for classical types. For classical types, yeah?
Yes.
Not for exceptional, you cannot do it at all, I think, yeah?
Well, I mean, I'm not an expert.
No, I don't think so. Yeah, for classical types, you can define the dual object to the Hecke algebra, which is some kind of co-ideal subalgebra, yes.
That's right. For exceptional types, you still have these co-ideal subalgebras, but they obviously don't.
There is no duality there.
Duality.
No, there is, yeah, okay.
Okay, more questions.
Ivan, what is, if these I quantum groups, what is the classical version of it? Like, is there some way to get the type B and type D some, I guess, the Q equals 1 version of that Hecke algebra?
I need to think a little bit.
Yes, I think so. I mean, you can have actually you can have so if you take something like GLN or plus M over GLN cross GLM and take so the symmetric space,
Mhm.
it's dual to so there is gonna this is gonna be dual to Y group of type B in some sense.
It's like the way that the vowel group of type B embeds into the vowel group of type A2N or something is the intuition.
Right. So you have basically it's I mean it's going to be a product product of two GLNs. So
Yeah.
Okay. Why do I get a message that Vasily Krylov raised a hand?
Yeah, I occasionally raise the hand.
Okay. All right, let me pause the recording and see if there are questions then. Okay, maybe we should try to resume.
Okay. So, so this is going to just be the last part of my talk. This is section 4, the quantum coordinate algebra. Which in Janssen's book is denoted K sub Q and then G. So the motivation for this in the classical setting is the following. So it's kind of, I mean, it's maybe a little bit backwards to think about it, but this is just how it has to be, because in the quantum setting, we start with just the Lie algebra. And in the classical setting, we get from this a group G, which is connected, and we can take it to be simply connected. Semi-simple algebraic group. Over our field K. And so this group, it has a coordinate ring, since it's an affine algebraic group, which is the ring of regular functions on G. So I haven't written a sub Q yet. So this is all just the classical setting. And I have a few things kind of related to this coordinate algebra. So I have derivations on G. So these are the endomorphisms of the coordinate algebra, which act as derivations. And then inside of this, I mean, derivations are a Lie algebra. I mean, end of KG is a Lie algebra by commutator. Derivations are preserved by commutator. And then I have a sub Lie algebra of all derivations that's just given by the left invariant derivation. So this is X in der G, such that if this commutes with left multiplication acting on functions for all G and G. So this is one version of, or isomorphic to your favorite version of, the Lie algebra of G. So if you didn't start with the Lie algebra appears as this left invariant vector fields on your group. And then this generates a ring of left invariant differential operators just acting on the group.
And here K has characteristic 0. Maybe we should emphasize.
Yeah, that's actually a really good point. So just from the beginning, 0. So yeah. So these are the left invariant differential operators. And basically because my Lie algebra is isomorphic to this Lie algebra of left invariant derivations, I get a map, which is an algebra homomorphism from U of G to left invariant differential operators on G. And because of this assumption that the characteristic of K is 0, it's a theorem of Cartier. That this is an isomorphism. So we have now, because differential operators act on the group, we get a pairing. Between U of G by just identifying U of G with differential operators and the coordinate algebra by taking a differential operator and then applying it to my function, but then evaluating it once. So just for the derivations, these are turning my derivations into point derivations at the identity. And then it's, I'm saying this is a theorem. I don't know if this qualifies or not, but I'm just stating it that way, that this actually is giving us an embedding from KG into U of G dual. So, I mean, all of this was just to get us basically to this point. I mean, we're in the quantum setting now. We start with our Lie algebra. We have a version of the enveloping algebra, but no group, so nothing to think about functions on. But in the characteristic 0 setting, we're able to identify the coordinate algebra of the group with some subspace of the dual of the enveloping algebra. So we're going to kind of start here now and work backwards to think about what will be the replacement for the coordinate algebra in the quantum setting.
And maybe it's important to point out that we can describe the image. It's subalgebra generated by matrix coefficients of finite dimensional representations.
Right. Yes. So for people who maybe are confused by this, I'm about to define matrix coefficients. But basically, this is kind of where we're going. We want to understand K sub Q of G or define K sub Q of G so that it's the analog of the image of the classical coordinate algebra in U of G star. So matrix coefficients, if V is a finite dimensional just U of G module, then if I have a vector in V and a functional in the dual vector space, which because U of G is a Hopf algebra is a U of G module, then I can define this functional on my Lie algebra, C sub FV, this is a matrix coefficient, by saying that if I plug in an element X of the enveloping algebra, this is, I take X, act on V by X, and then plug that into F, and this gives me a number. And it's clearly linear in X. So these are the matrix coefficients, and you know, I want to think about K of G not just as a subspace of U of G star, but as a subalgebra. So I need to have some multiplication, like a convolution product on U of G star. And this is, if I take lambda 1, lambda 2, two functionals, I'm just going to define their product as a functional to be that if I plug in an element U of the enveloping algebra, this will be the sum of lambda 1 of ui, lambda 2 of ui prime, where for u in U, such that delta of U, so the co-multiplication applied to U is this sum of ui tensor ui prime. So I'm using the co-multiplication kind of backwards to define this multiplication on the dual of the enveloping algebra. So the matrix coefficients and the multiplication on the dual of the enveloping algebra play nicely together. And this is a part of the following lemma, which gives us the following equalities. So if I take two matrix coefficients and multiply them together, this is actually the same as taking matrix coefficients for the tensor product. So this is for V in V, F in V star, W in W, and G in W star. And then I also have some additivity. C of FV plus C of GW is, I can take the sum of those maps acting on the direct sum of those two representations. And then I also have I have a unit with respect to this convolution product just in U of G star, and that's the co-unit, which is a functional on U of G. So the co-unit is in U of G star, and multiplying a functional by it gives me back the functional. Moreover, actually, the co-unit is a matrix coefficient because it's the matrix coefficient for the dual basis vector and the basis vector in the trivial module. Because the co-multiplication tells you how the enveloping algebra acts on the trivial module. So we have these nice relations for the matrix coefficients. You know, the proof of this lemma is just an exercise in understanding the definition. And so the main point of all of this is that now we can describe, let me just reiterate what Yvonne said, that the image of KG in U of G star actually as a unital algebra with respect to this convolution product spanned by matrix coefficients, but matrix coefficients of all finite dimensional U, or let me just say G modules. So I won't write this out, but it's like, why is this spanned by matrix coefficients? Well, this is some consequence of like the algebraic version of the Peter-Weyl theorem. And that's using G semi-simple, and then G was assumed to be simply connected. So that means that actually all U of G modules, so all of the finite dimensional modules for the enveloping algebra are actually modules for the group. And that's why this image is actually all finite dimensional U of G modules. So that was all classical, but basically everything can be redone, but backwards in the quantum case. So to define KQG, there is no G, but we have, I mean, there's no G to take functions on, but we have the following definition. KQG is the unital subalgebra of, now I take the quantum enveloping algebra, its linear dual, and I still have the same convolution type product because it's just defined in terms of the co-multiplication, which I have for UQ of G. And I can take the span of matrix coefficients, but then the usual issue comes in that I don't want matrix coefficients of all finite dimensional representations. I just take modules in type 1 finite dimensional representations. And then the point is that the trivial module is type 1, and so that's why I have a unit in this case. And part of the whole point of this, at least if you're starting just with the enveloping algebra, is that the dual of the enveloping algebra is not a Hopf algebra. And that's because, so here's our upshot of defining things this way, is that if we have this multiplication map from U tensor U to U, and that gives us a dual map from U dual to U tensor U dual, but this properly contains, when you leave the finite dimensional case, U dual tensor U dual. So it's actually a lemma that if I take mu upper star, the co-map to the multiplication map, and restrict it to this quantum coordinate algebra, which is just the subspace spanned by matrix coefficients of type 1 modules, type 1 finite dimensional modules, then I'm going to actually land in KQG tensor KQG. And so that's partly the reason for introducing this and not studying just the whole dual of the enveloping algebra from the start, is that this allows us to, so we can define a co-multiplication for KQG. There's also going to be a unit or a co-unit and antipode. So KQG ends up being a Hopf algebra. So it's a worthwhile calculation just to check that if I take a single matrix coefficient in this ring and apply this sort of mu star to it, then it's going to be able to be expanded in terms of sums of tensors of matrix coefficients. So a priori, mu star just takes KQG to U tensor U star, since this is just a subspace of this, but it actually lands here, and that's a check. But that's something that's nice. So the other thing is like, so I'll just say proof is an exercise. The other thing is that this is a really mysterious algebra. It's just the algebra generated by some elements. So we don't know exactly what relations these elements will satisfy. But the reason that this is even in this section is that we can get some relations from the R matrix. So what is this algebra? It turns out that we can determine some relations from using R. And what's the idea? Well, let V be I guess really let V and W both be type 1 modules for the quantum enveloping algebra, and choose a basis V1 through Vn for V, and F1 through, actually I'll write it different, V1 star through Vn star, a dual basis, and W1 through Wm for W, and W1 star through Wm star for W star. So we choose bases and dual bases for these two finite dimensional representations. And then for notational purposes, I'm just going to write Cij as this is the matrix coefficient corresponding to Vi star and Vj, and then D Ij is going to be dwi star wj. So I noticed that there's some stuff in the chat. If I'm doing something wrong, if people have questions, let me know. If it's nothing, I'm just going to ignore it.
Well, we have fans of non-type 1 representations. I'll deal with them.
Okay, that sounds interesting, but I'm going to ignore it. So I then recall that I have this map RWV from W tensor V to V tensor W, which is an isomorphism sending, and I'm just going to write it down. I chose a basis, so I can write this down in this horrible way of a sum over indices H and L of R, Ij, HL, VH tensor WL. And, you know, I mean, how does this work? So just notice then the following lemma says we have the relations, the following relations hold in this ring of matrix coefficients, my quantized coordinate ring. On the left-hand side, I have a sum of RHL, RS, DL, I, C, HJ. And on the right-hand side, I have a sum HL, R, I, J, HL, C, RH, D, S, L. So what is this? So I have matrix coefficients with respect to V and matrix coefficients for W, and then I have my braiding, the matrix entries of my braiding between W and V appearing. And so I have a bunch of relations that look like this, which tell me relations that are satisfied by the matrix coefficients. And I mean, I'm just going to say some brief thing about this. So to see this, use something that I wrote before, which is if I have WL star tensor VH star WI tensor WJ, this is equal to C WL star WI times C VH.
Something wrong with indices on the left-hand side.
Yeah, sorry.
W should be V.
That should be V. J, and this should be VH star VJ, and that's equal to, so my W's I rewrote as my D's, just to try to simplify things a little bit, and then my my V matrix coefficients I wrote as my C's. So from this equality, if you observe that U acting on Wi tensor Vj, this equality tells us that this is equal to D Li C Hj of U WL tensor VH. So I'm just expanding out the action of my element u by using these matrix coefficients to read off those terms, summing over h and l. And then I can expand both sides of this equation R of u acting on wi tensor vj and u acting on R of wi tensor vj. So these relations that are satisfied above, that I'm in between my matrix coefficients that I'm reading off of the entries of my R matrix, they come from the fact that the R matrix commutes with the action of u, and then this kind of weird, not weird, but this relation for tensor products of representations in terms of matrix coefficients. So if we just expand both sides of this equation and compare coefficients, we'll get the relations. So
does this relation trivialize in the classical case?
Right. I mean,
well, it's not. It says that the algebra of functions is commutative.
So it's
So
somehow
kind of so when we say that R matrix is trivial, it basically means that the coproduct on U of G is co-commutative, and so the dual algebra is going to be commutative, and that's what these relations are going to say, which is a nice exercise.
Thank you.
okay. Are there any other questions? So this is the last thing that I'm going to write. Let me just say an example. If we were thinking about KQ of capital SL2, and I took V is equal to W is equal to this first fundamental representation, the quantum analog of the vector representation. And so up above, I wrote my basis for this in terms of V, which I'm going to relabel as V1, and FV, which I'm going to relabel as V2. And then exercise / example, because nobody wants to watch me do this, is that you use RVV to deduce the following relation. So I have C11, C12 is Q, C12, C11. I have C11, C21 is Q, C21, C11. I have C11, C2, or C12, C22 is Q, C22, C12. I have C21, C22 is Q, C22, C21. I have C12, C21 actually commutes with C21, C12. And I have C11, C22 minus C22, C11 is this Q minus Q inverse that's appearing everywhere always times C12, C21. And then, also the following relation holds, or let me say it this way, sorry. So that's the exercise is to derive those relations. And then let me just finish by stating two facts. One is theCij's generate this ring as an algebra because, well, as I mentioned above, taking direct summands and tensor products plays well with matrix coefficients. And the symmetric powers, or the quantum symmetric powers, the LNs, are all summands of V tensor N. And all finite dimensional type 1 representations of UQ SL2 are going to be direct sums of irreducibles of this form. And then the other thing to notice is that if you add the quantum determinant is equal to 1 relation, then this gives a complete list of relations, meaning that the quantum coordinate algebra of SL2 has a generators and relations presentation where you just have the CIJs as the generators, these relations, and this relation. Okay, that's all I have written. I can add more if people have questions, or other people can add stuff if people have questions.
Okay, so let's thank Elijah for the talk.
Thank you for listening.